So my name is Michaela King, and I'm a research scientist here at the Polar Science Center at University of Washington. And one of the projects that I'm involved with is the Greenland Ice Sheet Mapping Project, or GrIMP for short. GrIMP, the purpose of the project is to create and maintain a benchmark set of data products that are used for observing features of the Greenland ice sheet, and then also monitoring ongoing changes and metrics of stability. Let's see, this is most of the GrIMP data products are hosted at NSIDC. So this is kind of the homepage for that. As part of GrIMP, there have been developed a series of Jupyter notebooks, right, which we've been working with this week, that kind of walk you through all the different functionalities, make it a lot easier to access these really large data sets, subset them, plot them, explore them. There's even a notebook for if you're more comfortable working in like a QGIS environment, you can select the data products you like and sort of organize a nice QGIS project to download and work offline from, or in the cloud as well. So let's start here. If we kind of scroll down, I've included some comments here that kind of walk you through if you were to work outside of this Hackweek with the GrIMP data products or on your own local machine. It kind of lists the commands that you would use to make sure your environment is set up to be able to utilize the full functionality of the GrIMP products. And so before we begin with the normal imports, we're going to pip install two packages here that are developed specifically for working with GrIMP data products. So the first one being GrIMP functions, that's just a series of functions for the GrIMP data products. The other one you see is NISAR dev. So NISAR refers to the upcoming, it's a NASA satellite mission that uses synthetic aperture radar to monitor changes on the Earth's surface, including over the ice sheets. And so GrIMP, once NISAR is launched and the data start coming in, those will fall under the GrIMP umbrella. So those will be part of the GrIMP packages. And then you can use these same tools to work with those velocity products as well. Yeah. Oh, I'm sorry. So if you go into the shared public if you're in your home directory on cloud, shared public, there should be a day 4 folder. Yeah. So don't do this again. If other people's tutorials earlier the week, as Jess said, that's not best practice, but that's where you find it. And then it'll be book tutorials and then GrIMP. Yep, absolutely. If people need a minute, I can kind of pause while people find it. Are we okay? Or do we need another second? I will take the silence as we are all on board. Okay. And so it'll spit out a bunch of, once you do the pip installs, it'll kind of spit out a bunch of text saying, all right, blah, 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 blah. We've got your stuff ready to go. And then we'll do the normal imports here. So a lot of these packages you've seen throughout the week. You also notice that there are a few like ice picks here. And so not only today are we going to demonstrate some of the GrIMP functionalities, like plotting some of these ice sheet imagery and velocity products, but we're also then going to be bringing in some ICESat-2 data alongside GrIMP data products in a way to better show how incorporating ICESat-2 data alongside other geophysical data sets and variables can help us better understand the underlying processes in the observations that we're looking at. So doing some real science stuff today. Okay, and then this command here, this is just using authenticating to Earth data so that we can access NSIDC data. And then we do have a YouTube page. There's only a couple of videos on there right now, but we'll continue to populate that, that walk you through tutorials, some of the existing tutorials in a little more detail, explaining things just like binder and the environmental setup and things like that. So feel free to check that out on your own time. All right, so the first bulk of what we're going to walk through today is we're going to use this GrIMP function here. This is going to bring up a Explore tool that you can look at the different GrIMP data products that are housed at NSIDC. So it might take a few seconds to run, and it's going to bring up an interactive panel that you can click through the different data products and see how many different files are associated with each. Anytime now. While this runs, I can show you kind of what it looks like. It might take a minute if we're all trying to do it at once. Okay, so if it's still running in your notebooks, I just want to kind of show you what that looks like. So it'll be a panel here that the headings are the different NSIDC data products. So each of these numbers correspond to either like an imagery product or a different velocity data set. Let me check in how we're going. All right, we're good now. And you can further filter by the exact product that you're interested in. If you scroll down below the search button here, you'll see there's a product key. So this explains what each number corresponds to. So right now it's automatically selected on this 723. Let's find 723, and these are the SAR image mosaics. Okay, cool. Let's say we want to look at the annual velocity. So this is going to be how fast the ice is flowing over the entire ice sheet, and over an average over the year. So an annual average of ice flow speeds. So we could click on that. Let's say I don't want to adjust the first and last date at all. I just want to search. Do that. And then we see that this list over here updated. I don't know. Yeah, I know. This is exactly why Jess was like, don't do that. Okay, and so we have 7 annual velocity maps that are available to download. So this, you can kind of click around in here, search, and then see exactly how many data products are available for each of these, or how many files are available for each of the different data products. So kind of neat. Okay, and so far we haven't actually downloaded any data. We are going to be utilizing a lot of the functionality that's available through working with cloud optimized geotiffs. So a lot of the GrIMP data products are formatted as cloud optimized geotiffs. These have a couple benefits. One, all the header information is stored at the beginning of the file. So you can get the information on the size, variables, how the data is organized, all with just a simple read of the header information rather than multiple iterations of a read execution. Also, a lot of the GrIMP data products, the cloud optimized geotiffs, they are tiled, which means that the data is kind of chunked, sort of like stored as like chunks, like a checkerboard, which makes it facilitates a lot faster reading of like subsets of the data. And so here, this little note, this is if we were just querying NSIDC directly and weren't working with any local downloaded data, we would use these functions here. I've just included those in the note that you can use those on another time. For today, for the purpose of the tutorial, we're going to be working with locally stored data just so that it works for everybody. But you would use these functions then to query the URLs to the actual data files that you want that are at NSIDC. Okay. So instead, we are then going to be reading in some data that are stored locally. So if we run this here, what this does, what we're doing is we are creating an object to store the velocity data sets. Here, we're looking at just one slice of an annual velocity data product. And we can quickly look at the size that the data would be if we were to download it. We can look at the dimensions, the coordinates, we can get geospatial information. Anytime that you want more information about the different arguments that you can make in some of these GrIMP functions, if you just click to the left of the parentheses and do a shift tab, you can get more information then on the different arguments and inputs that you can use. One thing that I adjusted kind of from the default on this read series from TIFF function here is the overview level. So this argument says what's the resolution of the data that you want to look at. A full resolution, I think, is -1 is the default just for today. So we're not all working with tons and tons of data. I have overview level 1, which is basically 1/4 resolution, I believe 1/4 resolution of the native product. All right, so with this one annual Greenland-wide velocity map, that's looking at a quarter resolution, it's about 75 or 74 megabytes. So again, we haven't actually downloaded any products yet. We can also then display what this data looks like. So if we want to look at a velocity map of Greenland, there's also a function display vel for date. So this is underneath the GrIMP functions that we pip installed at the beginning. And you can insert the date that you are interested in, and it will find which of those time slices are closest to that date and plot that. Oh no, what did I do? Okay, little progress bar here as it loads, and then you can look at this velocity map of Greenland for the 2021, the annual average speed the ice is flowing. And so the areas where we're getting kind of blue to the purples and brighter pinks and reds, that means the ice is flowing faster. And so looking at an ice sheet wide velocity map like this, you can kind of get an idea of how the ice flows slowly in the interior, and then it speeds up as it kind of goes down through these outlet glaciers before it eventually terminates, breaks off as icebergs in the ocean. So a lot of cool stuff to see there. Again, these files can be really large. So just for today, I'm looking at a quarter resolution, but if you are downloading multiple, let's say 6 day, there's 6 day velocity maps. If you want several years, every 6 day Greenland wide velocity map, you're looking at 300 or so gigabytes of data. So it's important to be able to kind of interactively explore the data and do subsets or time slices and see first how large the data set is before you decide whether or not you would like to download. There is an interactive region of interest selector tool that, again, if you were querying the data at NSIDC and not working with local download data, you would use these functions here. For today, I've already kind of found an interesting area where a glacier is doing something funky for us to look at. So these bounding box here, this corresponds to that region. So we're going to run this manual selection today. But again, you could interactively kind of highlight an area, decide whether or not it's interesting, rerun it until you're happy with your region of interest. Okay. And so this subset vel, so I subsetted that velocity map with the bounds that we provided. And then we can see what the size here would be. This is a very, very small style because remember, initially I'm saying I only want a quarter resolution of the native data. So really small. You would probably want to have full resolution if you were actually looking at just a small region of interest. But this just goes to show how you can do a subset, see then how large the data is. Look again at the bounding box or the different bands of data. If we look under the band information, Vx, Vy, Vv, the Vx, this refers to the displacement of the ice in the x direction. Then again, the y direction or Vv, this is like the magnitude, so how fast the ice is flowing. Okay. So there are also functions included that if you're happy with the data that you subset, you plotted it, maybe you've looked at the file size, you're like, yes, this is what I want. There are tools then and functions that you can download to a netcdf file for offline exploration or further analysis. I've already downloaded the netcdf file that we're going to work with today, so we don't need to do that, but I've just included the commands here that you would need for that. Okay, so today then we're going to be looking at a glacier on the kind of the southeast, central east part of Greenland called Steenstrup Glacier. And so this function here, read series from netcdf, so we're going to read in the data that's already been downloaded as a netcdf file. So run that. All right, and we just want to confirm, I just kind of as a sanity check, want to make sure that it is kind of the data that I like. All right, it's that velocity series object. In the netcdf file that I've already kind of downloaded for our tutorial today, we're looking at 7 time steps. So we're looking at the full range of all 7 annual years that we have. And I had downloaded it as a full resolution. So you kind of notice that there's a lot more, there's the larger index in the X and Y direction because I'm not downsampling it like I did in the example above. So still we haven't, in theory, we hadn't downloaded any data. We can still plot it without actually downloading data. So we're going to do that here. There's, again, this function, if you remember from above, when we plotted the entire Greenland-wide velocity, there's this display velocity for date. But instead of actually specifying one date, I want to look at the full 7 years of data for this subsetted region. Okay. And so the glacier, Steenstrup Glacier, is this kind of one running from the top left to the bottom right. The brighter greens mean the ice is flowing faster, kind of looks like what we'd expect, moving faster as we get closer to the margin. And then the titles then refer to each year. Now, it's kind of hard to look just at this and understand what change is going on. And so there's also an interactive inspection tool that we can run that allows you kind of click on different areas of the glacier and see through that 7 time steps that we've downloaded how that's changed through time. And so if I click close to the front of the glacier here, we'll see that the time series is showing the velocity and how that's changed from 2015 all through 2021. And so one thing we noticed is that this glacier has accelerated quite a bit, right? So from like 2019 to 21 especially, and definitely in like 2020, there was a really big acceleration event, which means that ice is flowing a lot faster than it was in the past. It's over doubled in speed near the front, so about less than 1,500 to over 3,000 meters per year. So a really big change in a short amount of time, very unusual for how rapidly glaciers can change in Greenland. Another way to look at this is using the anomaly function. And so there's a built-in function that you can quickly plot the anomalies. And the anomaly will calculate each time step minus the mean over that entire time span that is included in that data file. So in the example here, we have 7 annual time steps. So each anomaly will be the difference between that time step and the mean over this 7-year period. So if you had a longer time period and ran the anomaly function, it would be the difference between that time step and the mean over that longer time period. Does that make sense? Okay. Okay, and so here's what this looks like. Areas in the blue mean that the speed in that year minus the mean it's slower relative to the mean because the mean is larger, so negative number. Where you see reds, that means that it's flowing faster than the average over that 7-year time span. So we really see a big difference between like 2018, 2019 is pretty close to the average, right? We don't see much color at all. So really from 2019 to 2020 is where we saw kind of a big jump. So a different way of looking at when that change occurred, right? And so I mentioned that we're going to incorporate ICESat-2 data at some point, and so that's kind of where this comes in here. Because if we're looking at how glaciers have accelerated over time, as glaciologists, one thing we want to understand is how that impacts different variables such as the ice thickness. And this occurs because ice in glaciers, they're what's called like a viscoelastic material, where you can kind of imagine silly putty. If you spread it out really quickly, it's going to sort of stretch out, it's going to thin. So if a glacier is accelerating, it's moving faster, and the supply of upstream ice cannot compete with how rapidly it's being pulled apart, you're going to see thinning, or that's what we would expect to see. So now what we're going to do is we're going to read in ICESat-2 data over this area of interest from 2019 and 2021 and see if we see thinning in the ICESat-2 data that can kind of confirm that there was a lot of dynamic thinning that took place. I've included some code here using like IcePix, where if you wanted to query, we're going to be looking at the ETL06 data product, so the land ice data product. If you wanted to look at that, wanted to access this within the bounding box we're looking at, you would run this. We're going to be just today locally using Ben Smith's function. He's a research scientist here at UW as well, just for reading in the ETL06 land ice products. So this is just the full function. I've had it written out here for reference. Okay. And then we are going to be reading in, again, 2 files that I've already have downloaded locally for us today. This is going to be looking at the track that goes across our glacier in 2019, and then again in 2021. So really getting on either side of this dramatic change we see to see, in fact, how much thinning occurred, if any at all. Okay, and then finally, we are going to then plot a bunch of things together. We're going to look at our glacier of interest, how much thinning or how much acceleration has occurred, and then see how the ICESat-2 tracks, what they can tell us about how much thinning occurred across that track. So then if we run this. Okay. And so the figure here on the left, so this is a zoomed in version kind of at the front of that Steenstrup Glacier area that we are looking at. The teal line corresponds to the ICESat-2 tracks. And then also the underlying color, like the reds on the glacier, this is showing the anomaly map. So I'm plotting, if we go up, the same function we've been using here, this display velocity for date. We are using that after this Bell anomaly. So you could just display the native velocity, or you could use the same function to display the velocity if you're wanting to display the anomaly. So it's just whatever you apply this function to, whether it be your velocity series or the anomaly, or there's even a function for mean velocity, that'll be kind of the variable that plots. And so we're plotting the velocity anomaly for 2021. So looking at how much faster the ice is flowing in 2021 relative to the mean. And then if we look at just this sample of this ICESat-2 track here in the red, kind of pull that out, and we're going to look at these 2 years, the June 2021 and then 2019 and 2021. We see that in fact across this trunk of the glacier, there's been quite a bit of thinning that's happened. On the right y-axis, I've also then differenced these two tracks just so you can kind of better see how much thinning has occurred. And it's anywhere from about 30 to over 50 meters of thinning just in the course of 2 years. And so for reference, I think this glacier back here is like 600 to 750 meters thick. So this is a pretty substantial percentage of ice loss just in a short amount of time. And so I hope some of these examples today kind of showed not only the different functions that you can use within GrIMP, but then also things you can learn about ice sheet change from bringing in together things like velocity and elevation change from ICESat-2 together. And then Ian Jockin is sitting over at this table here. He developed most of the GrIMP tutorial notebooks that are available on the GrIMP webpage, and is the PI on the GrIMP project. So you can, if anyone has questions, you can either ask me or Ian. We'd be happy to help more. So thank you. Is there any questions?
Hey, thanks for the tutorial. I'm sort of new to this project, so I was just wondering, you're not using any ICESat-2 to generate this velocity product at the moment, right? I'm curious what data products are being used.
Right, yeah, so all the velocity data products all come from this GrIMP project, which I guess that's kind of redundant, GrIMP project, but the Greenland Ice Sheet Mapping Project. So it's a totally separate suite of data products, but I just was showing an example of how combining those velocity products with ICESat-2 or in research especially, is used a lot to be able to kind of put a bunch of different changes together to understand what's going on. Yeah.
What specific like satellite missions?
Oh, okay. Yes, good question. So if we go, sorry, I misunderstood your question here. We are looking at the annual velocities, which is a combination of SAR imagery from like Sentinel-1, that's a European Space Agency mission, as well as Landsat optical velocities. And so this mosaic, Ian could probably speak a little more detail to that, but it kind of combines the optical and radar velocities together to get a nice annual average velocity map for Greenland. Yeah. Is that? Any other questions? Oh, yeah.
How the velocity from these data products compare to its live velocities? Are they overlapping?
There might even be a notebook where it compares the two, or is that no? It is really it depends what area you're looking at. Its live has basically like any pair, any image or radar image pair that'll have like a velocity estimate. It does maybe less smoothing or filtering. So you might see more noise compared to like the Mosaic GrIMP products. But that's something that some areas that are really similar and some they're quite different. So you'd have to kind of play around and click on your area of interest. If there's a certain area that you're looking at for your project or just outside research and want to ask us more about it, we probably could give you some more insight too.
I can add a little bit to that. I mean, ICESat generally is taking the Landsat pairs or the Sentinel pairs as they come off and processing them and spitting them out right away. We more or less process the same data, but we aggregate the data and produce time series that are more consistently done. So like for a point here, the most you could get would be like 400 points, which is every 6 or 12 days from Sentinel. With ICESat, you'd get thousands of points, but they're all going to be a lot noisier because they haven't been averaged and smoothed together as much. So our products are more all, except for the TerraSAR, individual scenes come out on a full Greenland grid, whereas the ICESat things are individual data take. There are some mosaics, but they're by and large mostly these data take individual products. So it's kind of like the difference between a level 2 and level 3 product, or maybe level 3, level 4.
That's a good way to put it. Yeah. All right.
Hi. So ever since Sentinel 1B went down, how has that affected the final product? Like you're talking about smoothing out the data sets,
Yeah.
but the aggregation must have changed, or you're using like RadarSat or something else for that?
Yeah, so for a while there, we were getting like 6-day. You get velocity maps every 6-day, and so that depreciates every 12 days now. So the temporal resolution has been impacted. But luckily, I mean, ICESAR should be upcoming next year, and so that'll be kind of help contain or maintain a continuous high resolution time series.
Okay, is there any substitute data set that is being used to kind of compensate and improve the temporal resolution?
Not with the SAR velocity mosaics. It's just instead of being able to get velocity maps every 6 days, it's just every 12 days for the time being. Yeah, there's really not over the ice sheet wide, there's really not another like mission or radar product that can kind of fill those gaps consistently.
Okay.
But yeah, there's also, and Ian mentioned, there's also the like TerraSAR Tandem X velocity maps for individual glaciers. So that's another. It's not what is that? 12 days is the TerraSAR. I mean, it varies, I guess, by region, but that could potentially help fill some of the gaps too, depending on the area you're looking at.
In many ways, the monthly products represent the sweet spot because they include all the Landsat, all the TerraSAR, and all the Sentinel data, and they're averaged down. And when you compare that with the 6 or 12-day data or the TerraSAR series, usually you don't see a lot more detail in the finer time resolution. And to the extent that you do, it's noisier, so you can't be sure that it's noise or signal. Mm-hmm. The only case where I think the higher resolution data would really be advantageous if you lost a big part of the glacier all of a sudden and you had a step increase in speed, like maybe if we caught that particular calving that or speed up that Michaela showed. But in general, even on Yak 7, when I compare the monthly, I'm not seeing a whole lot more information in the finer res data.
Okay, thanks.
But great question. Yeah, thank you. Wow. Yeah, awesome questions. Okay. I think that's it. All right, well, thank you everybody for paying attention for the third tutorial.